Conservation of mass in Lecture 1 in Topic 3. We have learned so far that mass is an extensive property that is conserved, and this general form of conservation applies to mass. This form that we have written is very specific for mass and comes from the general form. When we apply this equation to a batch process in a closed system, it takes a form that we call integral form, as you see here. Suppose that the duration of time of the batch process for which we want to write mass balance equation is delta T hours, say from 8 a.m. to 10 a.m. This first term is the mass that has crossed the boundary before delta T or before 8 a.m. and we call that feed. This term is the mass that will cross the boundary after 10 a.m. or after delta T, which we call that stream product. The third term is the mass that is generated or consumed inside the system during delta T or between 8 a.m. to 10 a.m. Generation or consumption for total mass is always zero for all systems. However, if we have reaction in the system, in some specific circumstances when we write the equation for a component or a species in the system, this term may not be zero. For example, you burn 200 grams of wood. During the combustion reaction, 50 grams of oxygen is taken from air. The product consists of exhaust gases, mostly CO and CO2 and water vapor, as well as solid ash that remains. The total mass of the product must be 250 grams. It is impossible that mass is produced or consumed during the reaction. Of course, if we have nuclear reaction, which is a different story, and in this course we do not address that, that might be different. If you write the mass balance equation on oxygen, it will be a different story. 50 grams of oxygen has gone in as feed, and there is no oxygen in the product since oxygen has been consumed. Therefore, we have a consumption here since we applied this equation to a component in the reaction, like component oxygen. If we apply this equation to other components like CO or CO2, we will see that we have non-zero generation in those cases. For a system that does not involve reaction, which we call non-reactive system, the generation consumption term is always zero both for total mass as well as individual species or components involved. And therefore, you can see this term to be zero. Since mass balance on non-reactive systems are less complicated, we address them first in this lecture as well as a number of future lectures. Accumulation means how much mass has changed per time. In integral form that we have here, accumulation is zero. Since our terms must be either before delta T or after delta T, not during delta T. For example, this term, which is the feed input, happens before delta T, and this product term happens after delta T. So we have nothing that is happening during delta T, and therefore accumulation is zero. In example 1, you have added 10 grams of sugar to your cup that contains 200 grams of coffee. At time 0, you start stirring your coffee for 10 seconds until all the sugar dissolves. We would like to write a mass balance on total mass. So we consider the mass that has crossed the boundary before 10 seconds. We know that 200 grams of coffee is already in the cup, so it has already crossed the boundary, and 10 grams of sugar is added, so that crosses the boundary as well before delta T. We would like to know how much coffee is inside the cup after the 10 seconds that is going to cross the boundary as we drink it. Let's consider that M. So M is the product. This is equal to 0. And we have the amount of M as 210 grams, as shown in the lecture note. In example 2, with batch operation, we assumed 1 pound of jam to be produced. Delta T here is between 8 a.m. and 11 a.m., which included crushing of the strawberries and water removal by heating. During delta T, we had both batch and semi-batch processes. For the sake of mass balance calculations, we drew the flowchart assuming a closed system during delta T, that is between 8 a.m. and 11 a.m. Before 8 a.m., M1 and M3, strawberry and sugar, cross the boundary, and then at 11 a.m., M2, which is the water, and 1 pound of jam cross the boundary as products. Of course, this is what the flowchart says. Definitely, the assumption on M2 does not match reality as far as how water has crossed the boundary. But if we look at all the water removal between 8 a.m. and 11 a.m., it is correct. In drawing a flowchart, these kinds of assumptions that facilitate calculations can be made. So here we can write M1 plus M3, which is the feed, minus M2 plus 1 equals to 0. Another form of mass balance equation is differential form, which is appropriate for continuous systems, which are obviously open systems as well. Here we consider what happens in the system at an instant of time dt. Unlike delta t in integral form, dt is a very short time in the order of fraction of a second. During dt, mass that is crossing the boundary as input is here. At the same time, on the other side of the system, mass is crossing the boundary as the second term. So the amount of mass that is crossing the boundary with input, we can consider it as m dot in times dt. M dot in is the flow rate, which is mass per time. When we multiply it by dt, that becomes mass. The mass crossing the boundary with output would be m dot out times dt. And as we said before, if the balance is on total mass, the generation or consumption is always 0. And if we consider non-reactive system, the generation or consumption term even for a component will be 0 as well. Let's write that 0 here. In this time dt, an amount of dm may accumulate in the system, so we write it there. If we divide both sides of the equation by dt, we will have m dot in minus m dot out plus 0 generation consumption equals dm over dt. This will be the differential form of mass balance. For a steady state, accumulation will be 0. It means that this term, and therefore we will end up with only m dot in minus m dot out equals to 0. Consider the production of jam example at a steady state with 60 pounds per hour of jam produced or 1 pound of jam per minute. This process is a steady state, and therefore if we apply the differential mass balance, we will write m dot 1 pound mass of strawberry per minute plus m dot 3 pound mass of sugar per minute minus m dot out, which will be m dot 2 pound mass of water per minute plus 1 pound of jam per minute. This is equal to 0. It is important always to write the units with the notations and numbers in a mass balance equation. In example 4, we have accumulation since the system has different input and output flow rates. If we apply the differential balance, we will have 3 kg per second of input minus 6 kg per second of output equals to dm dt. So as you see here, we have accumulation. dm dt would be equal to minus 3 kg per second. The initial half-full condition does not enter when we write the mass balance equation, rather when we solve the equation as shown in the lecture note. In example 3, although the system is semi-batch, it has been assumed as a continuous transient with zero output. Therefore, this term has been assumed 0 and m in would be equal to V liter per second times 1 kilogram per liter, which is the density of water, and this would be m dot in that will go in the equation here, as shown with the solution in the lecture note.